We're going to look at the integrals of exponential functions. So we have two formulas. The first is the integral of e to the x dx. So if you recall, the derivative of e to the x was just itself e to the x, which means the integral of e to the x is just going to be itself plus a constant. Now most of the time it's not just e to the x, it's going to be e raised to a function of x, and so we'll write that as e to the u, where u is a function of x, du. All of this is going to become a u sub problem, and so once I do the u substitution, my u and my du will fit into the problem, and I'll end up integrating this back to e to the u plus c. So here's a basic example. Let's say I'm starting with the integral of e to the 3x plus 1 dx. So my u is going to be the exponent. So if I make u equal to 3x plus 1, then du is equal to 3dx. And just like with normal u sub, if you're missing something for the du, I would normally put that on the inside and then balance it out with the reciprocal on the outside. So if I rewrite this integral, I have a 1/3 coefficient in front, integral of e to the u du, and based on our formulas, the integral of e to the u just goes back to e to the u plus c. And of course the last step is you have to go back and actually replace your u with what u is actually equal to. So 1/3 e to the 3x plus 1 plus c. And of course I could actually differentiate it to check my work. So if I differentiate it, e to the 3x plus 1 would end up giving me e to the 3x plus 1 times 3. Well, the 3 would cancel out with the 1/3, leaving me with e to the 3x plus 1, which is that integrand that I originally began with. So here's another basic example. Let's say I have the integral of 5x e to the negative x squared dx. So again, this is going to be a u substitution problem, where u is going to be the exponent, negative x squared. Du is going to be the derivative of negative x squared, which is negative 2x dx. If I look at the original problem, I have a 5x, but the du requires a negative 2x. So this 5 is not needed, and with properties of integrals, I can just pull numbers that I don't need out in front. And so now I'm going to have that 5 out in front, and then I'm going to put in what I'm missing for the du. So I'd have to put in a negative 2 on the inside, and then divide by negative 2 on the outside to balance it out. So if I rewrite this, I now have negative 5 halves, integral of e to the u du. So my integral would go to negative 5 halves, e to the u, which is negative x squared, plus c. And there's my antiderivative. Now sometimes they might look a bit more complicated. So take for instance, if I have the integral of e to the 1 over x divided by x squared dx. So first of all, notice that I can go ahead and rewrite this as e to the x to the negative 1 over x squared dx. Now, when you're trying to solve this type of problem, typically if there's only one exponential function, then normally your exponent is going to be your u, and somehow the rest of it's going to become du. And so that's what I would want to start with first, as just trying something to make it fit for u sub. So I'm going to make u equal x to negative 1, and if I differentiate, du then would be negative x to negative 2 dx, which is the same thing as negative 1 over x squared dx. So notice, I have that in the original problem. The only thing I'm missing is a negative in front, which I'm allowed to put in the missing coefficients that I need. So I'm going to put a negative on the inside and then a negative on the outside to balance it out. So if I rewrite this, I now have the negative integral of e to the u du, which is just going to go back to negative e to the u plus c, and my u was x to negative 1, and then of course plus your constant. So let's try one with trig. Let's say I'm looking at the integral of sine of x, e to the cosine x, dx. Well again, I only see one exponential function, that's at e to the cosine x, and then I have the sine x. So more than likely your u is going to be the exponent, and then whatever's left over will be part of the du. If that doesn't work, then try something else for your u and du. In this case, though, it'll work. So u is cosine x. Du is the derivative of cosine, which is negative sine. So the only thing I'm missing is a negative, which I can put on the inside, put on the outside. And so now I have the negative integral of e to the u du, which is just going to go back to negative e to the u, so negative e to the cosine x, plus c. So now that we've seen some examples for indefinite integrals, let's try a couple definite integrals. So my first definite integral is going to be evaluated between 0 and 1 of e to the negative x dx. So in this case, my u is going to be negative x. Du is going to be negative 1 dx. So I'm just missing a negative again. So now I have the negative integral of e to the u du. I'm going to go ahead and convert my limits. So if I take this 1 right here and plug that in for x, then my upper bound becomes negative 1. And if I take 0 as the lower bound and plug it in for x, then u would still equal 0. And so then the integral of e to the u is just e to the u, evaluated between 0 and negative 1. And using the fundamental theorem of calculus, I'm going to plug in the top minus the bottom. So negative e to the negative 1 minus negative e to the 0. Well, e to the 0 is just 1. So now I have negative e to the negative 1 plus 1 is the answer to the original definite integral. So all the problems we've seen so far have only had one exponential function. Let's look at a problem where we have more than one exponential function, and so we have to figure out a different way to do the u sub to solve this problem out. So I'm going to look at the definite integral from 0 to 1 of e to the x over 1 plus e to the x dx. So normally if I just had an exponential function, I could make the exponent my u. However, because I have multiple exponential functions here, I have to determine something bigger than just the exponent for my u. So if I tried to make u just x, all I'm doing is basically changing out the variable. I'm not actually doing anything to simplify the problem, which is the point of u sub. You want to simplify the integrand. So I'm going to look for something bigger, which means I'm going to look at this denominator as my u. So if I use u is 1 plus e to the x, and differentiate that to get du, then I end up with e to the x dx, which notice is the numerator of this integrand right here. And so rewriting this thing, I now have the integral of du over u. I'm going to go ahead and convert the limits again. So if I plug in my upper bound for x, I now have 1 plus e as my new u value. And if I take 0 and plug that in for x over here, I would have 1 plus e to the 0, which is 1. So 1 plus 1 is 2. And then the integral of du over u goes to ln absolute value of u, evaluated between 2 and 1 plus e. And using the fundamental theorem of calculus, I plug in the top number. So I have ln of 1 plus e minus ln of 2. And of course, because you have positive values, you can drop the absolute value. And of course, you could combine this into one fraction. You could make this ln of 1 plus e over 2 if you needed to simplify it further. Okay, last example. We're going to look at one with trig. So negative 1 to 0 of e to the x times cosine of e to the x dx. So again, I see more than one exponential function, which means I don't want to make the exponent my u. In this case, I'm looking for the inside function, and so the inside of cosine is e to the x. So I'm going to make that e to the x my u. And if I differentiate that, I get e to the x dx. And so the e to the x in front is my du. So if I rewrite this, I have the integral of cosine still there, u du. I'm going to go ahead and convert the limits. So if I take 0 and plug it in for e to the x, I get e to the 0 is 1. And if I take negative 1 and plug it in for x, I now have e to the negative 1. The integral of cosine goes back to positive sine. evaluated between e to the negative 1 and 1. And so now I have sine of 1 minus sine of e to the negative 1. I really can't do much with that except rewrite the negative exponent, so I'm going to leave it just like it is.